Good morning. I welcome you to this session of Thermodynamics. Before I start the class, I should mention one thing today, which I should have mentioned in the last class, that now we are discussing about the multi-component systems, but at the beginning of this course, I have shown the course curriculum where this part was not included. This should be made clear at this juncture, but at a later period it was felt necessary that some fundamental thermodynamic principles of multi-component systems and thermodynamic equilibrium and equilibrium of multi-component multi-phase systems are essential as a part of this course. So therefore this has been included, and that's why I will I am going to teach this, but at this moment I am not going to tell you the detailed syllabus or course curriculum for it, but I tell you in short that this will include a brief discussion or basic thermodynamic principles of multi-component system, which we are discussing now. Then I will discuss on thermodynamic equilibrium and equilibrium of multi-component and multi-phase system. This was not shown earlier or told earlier at the beginning of this course as a part of the course curriculum. So therefore I want to tell this before I start for today's lecture. So now let us start as a continuation of our last class discussions, where we ended in the last class. Probably if you recollect, we ended here that G, the Gibbs function of a multi-component system, can be defined as mu I in I. This is mu I in I. This was derived for R number of components with the help of the definition of thermodynamic potential, the definition of Gibbs function, and the Euler's theorem for homogeneous function. We defined this relationship, if you recall the last class, G as the sum of the mu I in I, from which we derived a uniform conclusion that for a single component system G is mu into N, which means mu, the thermodynamic potential, is the molar Gibbs function. That means the Gibbs function per unit mole, number of moles. So this we already discussed in the last class. Now today we start like this. If we differentiate this dg, then we get mu I dni, first term, I is equal to 1 to r, plus we get this ni d mu I. All right. So these are all at constant pressure and temperature. This is at constant pressure and temperature always. G at T and P, that we get this relationship. Okay. dg is mu I dni plus ni d mu I. Now earlier, if you recall, we had this relationship dg is equal to minus s dt. If you recall, we did it earlier when we defined the thermodynamic potential. Where from we got this relationship? Mu I dni, mu I dni, I 1 to r. So this we got by expressing G as a function of T and P, and then by recognizing the fact that dg is minus s dt plus v dp for a pure component, single component, pure substance. dg is minus s dt plus v dp. So this part is for the multi-component system. If we express G as a function of T and P, this we defined earlier. Now if we compare these two, then we can write s dt plus v dp. If we compare these two, dg, they are equal, that means this equals to this, plus summation of ni d mu I, ni d mu I, this as I is equal to 1 to r, I is equal to 1 to r is equal to 0. And this equation is very important equation. This equation is very important equation, and this equation is known as Gibbs-Duhem equation. Gibbs-Duhem equation. This equation is known as Gibbs-Duhem, well-known Gibbs-Duhem equation in multi-component system. So at constant pressure and temperature, now at constant T and P, Gibbs-Duhem equation becomes ni d mu I is equal to 0. That means for R number of components at constant pressure and temperature, summation of ni d mu I is equal to 0. This is an important relationship between the change in thermodynamic potential and the number of moles. Okay. Next, I will start a very, very important property which is known as partial molar property in a multi-component system, which is very important. As we know, for a single component system, a molar property is the property per unit mole. This molar property or this specific property, as we know, are defined for extensive properties, that means properties which are directly related to mass. The property per unit mass is the specific property. For example, specific internal energy, specific enthalpy, specific Helmholtz function, specific Gibbs function, specific entropy. Similarly, if you consider moles, okay, as the unit of mass, that is the amount of substance, indicating the amount of substance, as we know earlier definition of mole, then for a single component system, this extensive property per unit mole is the molar property. For example, the molar internal energy, molar Gibbs function, molar enthalpy, like this. But in a multi-component system, when there are number of components, this molar property for a particular component existing with other components in the system are expressed in terms of partial molar property. And we are going to discuss this partial molar property, how they are defined in a multi-component system. So, this to do, let us start with this partial molar properties. Let us consider Y an extensive property as a function of temperature, pressure and the number of moles. Let us R number of components, R number of moles. Okay? Now, as usual, we can write del dy, the change in y, as del y del t at constant p and n dt plus del y del p at constant t and n dp plus obviously sum of all the derivatives with respect to number of moles for ith component, where other moles are fixed, that is nj j naught is equal to I, and this summation extends from I is equal to 1 to R. All right. Now, if temperature and pressures are constant at constant T and P, temperature and pressure, we can tell that this change of this extensive property at constant T and P is therefore responsible for this del y del n I, this term only, these terms, not term, there are number of terms, T P N J, J naught is equal to I. Okay. All right. Now, after this mathematics, now we come to the definition of the partial molar property. The partial molar property for a component I is denoted as Y with a bar suffix I is defined as the rate of change of the extensive property of the system of R components with respect to the change in the number of moles of that component, for which we are going to define the partial molar property at constant temperature, pressure and other constituents, compositions of the J naught is equal to I, other constituents. Therefore, we see again the physical definition comes from this, that the partial molar property of a particular constituent I is the rate of change of that extensive property for which the partial molar property of the constituent is defined, is the rate of change of that extensive property with respect to the number of moles of that constituent for which the partial molar property is defined when temperature, pressure and the compositions of the other components remain fixed. This is defined as the partial molar property. This is the basic definition of the partial molar property of a component in a multi-component system. So, with this definition and the nomenclature for the partial molar property, we can write the change of any extensive property in a multi-component system at constant temperature and pressure is the sum of the partial properties. Sorry, here I have missed this term dni, I am extremely sorry, dni. So, y bar I, sorry, dni. So, therefore, it is a very, very interesting relationship that the change in the extensive property y, any extensive property y at constant temperature and pressure of a multi-component system consisting of r number of components equals to sum of the product of the partial molar property times the change in the number of moles of a particular component, and this summation extends from 1 to r, that is for all the number of components. So, therefore, this is a very, very important relationship. Now, if we consider that y, we get some more important relationship. Now, you consider y is a homogeneous function. Now, we exploit the Euler's theorem on homogeneous function. So, y is a homogeneous function, as we know y is a homogeneous function, homogeneous of first degree, homogeneous function or first degree homogeneous is a first degree homogeneous, rather I write here first degree homogeneous function in n's. Obviously, y is an extensive property, it depends upon the number of moles and it has to be at a first degree homogeneous function of n. That means the n is increased by a by some factor. That means if n is increased, if we consider dn I at lambda n I, then y will be increased by the same proportional factor lambda. That means it is the first degree homogeneous function in S. Then by Euler's theorem we can write that the function yTp is sigma del y del n I into n I. This we have already seen earlier, that is the Euler's function, that yTp, that constant temperature and pressure, okay, is equal to I1 to R del y. This is the first degree homogeneous function in n. Okay. So, therefore, we can write this becomes equal to del y del n I. Now, this del y del n I at constant temperature and pressure, obviously at constant temperature and pressure, and njj naught is equal to I. That means this becomes equal to y bar I n I. So, yTp is y by r n I. So, therefore, here also one important property comes, or important conclusion comes, that what is that? That the extensive property of a multi-component system at constant temperature and pressure is given by the sum of the partial molar properties times the number of moles. So, therefore, if I know the partial molar properties of each and every component for r number of components, then the sum of the partial molar property times the number of moles of the respective component gives the total extensive property. Now, from here again we derive a very important conclusion that for a single component system, for a single component system, therefore, we get y is equal to y bar into n. That means, y bar for a single component system is y by n. That means small y, that is the molar property. That means, for a single component system is the molar property, molar property, molar y. So, partial molar property is the molar y. Okay. So, this is a very, very important relationship for a multi-component system, for which for a single component system we get this. Now, with this as the definition of single partial molar property, now we just write the partial molar properties for different extensive properties. For example, we start with the partial molar volume. For example, for an ith component, we can write del V del n I at Tp Nj j naught is equal to I. Similarly, for U, we can write Ui for an ith component. The similar way we can write. Better we should write it. This will develop your practice. Nj j naught is equal to I. If we have to define the partial molar enthalpy for a ith component, then we should write this del H del n I at T P N J j naught is equal to I. Similarly, if we want to write the partial Helmholtz function for ith component, then we write del F del n I at T, P and N j, that is j naught is equal to I. All right. Similarly, if we want to define the partial molar property for the Gibbs function of the ith component, partial molar Gibbs function for the ith component, then we can write del G del N I at T, P and Nj, J not equals to I. All right. So, therefore, we can recollect this. But here one important thing is, see that while we define the thermodynamic potential, if you remember, this was also the definition of thermodynamic potential mu I. So, from there we can write the partial molar Gibbs function is the thermodynamic potential. This is, so there thermodynamic potential was defined by many relations. If you remember one of the last classes, the thermodynamic, where we defined the thermodynamic potentials, if we remember the thermodynamic definition of thermodynamic potentials, if you remember that we had many definitions for thermodynamic potentials, and one of the definitions for thermodynamic potential is the, well, one of the definitions for thermodynamic potential was the del G del N I T P N J. Now, it has to be made clear that the partial molar properties for other properties are not equal to thermodynamic potential. For an example here, if we express thermodynamic potential, okay, thermodynamic potential for chemical potential, not thermodynamic, sorry, I am sorry, chemical potential in terms of U, then you remember mu is equal to del U del N I at S and V. So far you remember S V N J J naught is equal to I. So this is not at constant temperature and pressure, very important. For I H, that means if you express chemical potential in terms of H, it was del H del N I at S and P N J, this is all right. That means it is not T and P, S and P. For Fi, with respect to Fi, it is the same differential del F del Ni, but not at T and P, rather T and V, and of course Nj J naught is equal to I. It is only for Gibbs function. If you recollect the definition of thermodynamic potential, you will see that it is only for the Gibbs function where we defined it thermodynamic potential in terms of temperature at constant, like this del G del Ni at constant temperature, pressure and Nj J naught is equal to I. Therefore, it is the partial molar Gibbs function which equals to thermodynamic potential. Very important. It is not partial molar Helmholtz function, not the partial molar enthalpy, not the partial molar internal energy, not the partial molar volume, which becomes equal to the thermodynamic potential. So Gi bar is thermodynamic potential. For a single component system, we know Gi bar is nothing but the molar Gibbs function, as we have already seen earlier. In the last class, Gi bar is G, or no, not last class, this class itself, we have seen that Y bar is the molar property. Just now we have seen that Y bar, that is the partial molar property, becomes for a single component is the molar property. So therefore, for a single component Gi bar, so I will not come, that means G bar is the molar Gibbs function, and that becomes equal to chemical potential. So therefore, for a single component system, the chemical potential becomes equal to the molar Gibbs function for that single component system, whereas for a multi-component system, chemical potential, not thermodynamic, I am sorry, chemical potential becomes equal to the partial molar Gibbs function. Again I am telling, for a single component system, the chemical potential equals to the molar Gibbs function, which is the partial molar property for a single component system. The word partial does not come there, it is only the molar property, molar Gibbs function. But for a multi-component system, thermodynamic potential becomes equal to the partial molar Gibbs function. Okay? So this is one very, very important relationship. Now, after this, I will derive some other very important relationship. Now you see that if we write, now you start that Y at T and P, we have seen, is sum of the Y bar N I at constant temperature and pressure. So this we have seen. So similarly, if we now in the same way as we did earlier for the Gibbs function, if we now make the differential at constant temperature and pressure, then what we get? Y bar y bar I dni plus ni dy bar I. All right, I 1 to r and I 1 to r. So, this is the relationship dy at constant temperature and pressure. So, therefore, we get that. Now, you see dy Tp at the constant temperature and pressure is this one. Now, by Euler's theorem, we can write one very important thing. Now, from the Euler's theorem, if you write by Euler's theorem, considering now by Euler's theorem, if you remember by Euler's theorem, we can write one important thing. But before that, we want to tell, earlier we derived that dy Tp is sigma yi dni at constant temperature. Just now we have discussed that dy Tp is sigma yi bar dni, I is equal to 1 to r. So, if you compare these two, we get at constant temperature and pressure, always this constant temperature and pressure thing is there, this is equal to 0. It is again one very important relationship. Just like ni dgi is 0, ni dg, d mu I is 0, ni d mu I is 0, similarly ni dy bar I is 0. So, it is one very, very important relationship among the partial molar properties and the number of moles. Now, if we use the Euler's equation, now I use the Euler's theorem, not Euler's equation, I am sorry. Now, Euler's theorem on homogeneous function, Euler's theorem on homogeneous function, as you know, Euler's theorem on homogeneous function. Now, considering that yi bar is a 0 degree, homogeneous, is a 0 degree homogeneous function of n's. Obviously, because y is a first degree homogeneous of n, first degree, we know, because y is an extensive property. So, y bar is del y del n for any particular component. So, from the dimension we see that if it is a first degree differential is 0 degree. So, therefore, partial molar property is a 0 degree homogeneous function of n. So, there if we put the Euler's theorem, we get 0 is equal to sigma n I d, sorry, 0 is equal to sigma n I, we can write del y bar del n k, here we take n k, T p and n j j not is equal to k. So, this is one of the again very important relationship, n k del y. And another equation just now we have derived that sigma n I, these two are very, very important relationship. Just now we have derived n I dy I bar at t and p is equal to 0. So, now we write these two equations again, that one is sigma n I dy I, little bit mathematics is there, so you will have to bear with it now. In multi-component thermodynamics, little mathematics is there, del y bar, that is the partial molar property, del n k, it is from the Euler's theorem on homogeneous function, considering the function yi is a homogeneous of 0 degree in n. Okay? These two are very important relations. Now, if we define a mole fraction x for an ith component as ni by sigma n, I is equal to 1 to r, then what we can write from this, that if we divided all the terms by sigma n, that means the total number of moles, then this equation becomes xi dy I bar is 0, and this equation becomes I is equal to 1 to r, and this equation becomes xi del yi del xk, well, t p n j J naught is equal to K is equal to 0. These two are sometimes very much used in multi-component system, where Xi is the mole fraction of the particular ith component. Okay. Now, we will use this equation for to derive some important relations, but before that I will tell you another important thing, that we know there are certain thermodynamic relations in terms of differentials or without any differential thing. For example, G is equal to H minus T. This is a thermodynamic relation which defines Gibbs function. Okay. H is equal to U plus PV. This is a thermodynamic relation which defines enthalpy. Now, this is valid for single component and multi-component system. For a multi-component system, G is the Gibbs function of the system as a whole, H is the enthalpy of the system as a whole, S is the entropy of the system as the whole, T is the temperature. So, therefore, H is equal to U plus PV is also like that for the system as a whole, for a multi-component system, also for a single component system. So, now I will show you that the same relationship can be expressed for a multi-component system in terms of the partial molar property of a particular component. That means, for a multi-component system, for the ith component we can write like this, Hi, that means the same relationship holds. That means, the partial molar Gibbs function is equal to the partial molar enthalpy minus T into partial molar entropy. Similarly, the partial molar enthalpy is partial molar internal energy plus P, which means the relationship which holds good for the thermodynamic extensive property as a whole for the system holds for the partial molar property of the ith component also. How can you prove it? Very simple, you differentiate this function with respect to Ni. It is very simple at constant temperature, pressure and Nj, all other composition which not equals to I. Similarly, this side also you do that, because we have to do the same operations on both the sides to maintain the equality with the same constraint T, P, Nj, J naught is equal to I. It is extremely simple. We are doing it at constant temperature and pressure, so T is constant. So, therefore, del S del N I and T, P, Nj, J naught is equal to I. And by definition, this is Gi bar, and by definition this is Hi bar, and this becomes T-Si bar. So, therefore, we see that the same definition G is equal to H minus the same relationship holds good for the partial molar property. In the similar way, we can also prove by taking the differentiation of H, by taking the differentiation of U and V at constant P and T for both left hand and right hand side, we derive the same thing. And another thing is that this is true for the differential, for the relationship in terms of differential. For example, you know a well-known relationship, thermodynamic relationship, del H del P at constant T is equal to V minus T del V del T at constant P. So, this is again one very important thermodynamic relationship in differential form. The earlier one was not in differential form. Here also we can show that del H, what we are going to show, that the same relationship in the differential form is also valid for the partial molar entropy of a particular component. In case of a multi-component system, this equation is valid as a whole for the system. That means where H is the enthalpy of the system, total enthalpy of the system, where V is the total volume of the system. Okay. For a single component system, there is no point of any component, so H is the enthalpy of the system, V is the volume of the system. So, this is valid for a multi-component system as a whole, and the same relationship also like the earlier one in terms of differentiation also valid for the corresponding partial molar property of any component del Vi del T at constant P. Okay. How to prove this thing? This can be proved. First, let us take a differentiation of, let us differentiate the left hand and right hand side with respect to Ni. That means what we do, we take like this del Ni at constant T and P. That means del Ni of this term, del H del P at constant t. That means that this term we are differentiating with respect to n I at constant t, p and n j, j not is equal to I is equals to, now this side also we will differentiate del v del n I with respect to n I at constant t, p and n j, j not is equal to I, minus at constant t and p, t remains constant, del del n I, okay, del n I of this term del v del t at constant p, okay, at constant t, p, n, j, j not is equal to I. So therefore we see that first what we do, we differentiate and left hand and right hand side with respect to the number of moles Ni for a particular component I at Tp and other constancy of the other number of moles, other moles of the other components. Then what we do, we interchange the differentiation, order of differentiation. This is possible provided these thermodynamic properties are continuous function. In a system, the thermodynamic properties are continuous function, it is a continuous function. So these are the properties, they are the continuous functions. So therefore in this case, the interchanging of the differentiation, the order of differentiation is possible. So I just change it and I can write del del p of del h del n I, well, at constant t, p, n, j, j not is equal to I, all right. So this term remains as it is del v del n I minus t, here also I change the order of the thing, del del t, that means I can write del del t of del v del n I. So del del p of this I can write at constant temperature and n, because constant temperature was there. So when I take del del p, the differentiation constant temperature in it. Similarly del del t, I have taken del v del n I, then changing the order of the differentiation, del v del n I at t, p, n, j, j not is equal to I, and this thing you just see like this thing at constant pressure and n, number of moles, constant pressure. Therefore you see what is this, del, this is h I bar, so del h I bar del p at constant t and n is equal to, this is what, del v del n I am sorry, it is at constant t, p, n, j, j not is equal to I. So this is the definition of partial molar volume minus t, then that is the partial, this is also partial molar volume Vi. So minus t del Vi bar del t at constant p. So therefore you see, if you compare these two equations, now we see that the equation is del h del p at constant temperature is equal to V minus t del V del t at constant. That means a thermodynamic relationship in differential form, which is valid for the system as a whole, a multi-component system, remains same if we express, that means the relation remains same if we express this in terms of the partial molar property. That means this, if this extensive properties of the system as a whole is replaced by the partial molar property of any component, the same relationship can be used. So all right. So therefore we see any thermodynamic property relationship which is valid for the system as a whole is valid for the partial molar property of a component, okay, of the multi-component system. Okay. Now next what I like to tell you, that we already derived something earlier which is a very important derivation, as you feel that this one. So you remember this derivation, that xi dy bar yi bar 0, xi del yi del xk. Now one very important thing for a binary system, sometimes for working, for the ease of working, the binary system, for a binary system one important thing, one few important equations can be made. For a binary system, consider a binary system. Binary system means two component system. Binary system means two component system. Two component system. Binary system means two component system. Binary system, two component system. Okay. So let we define component 1 and component 2. Let y is a extensive property. So we know that if y is an extensive property in a binary component system. So we can write y, as we know y is sigma, we know y is sigma n yi bar I bar ni, I is equal to 1 to r. So for a binary system we can write y is n1 y1 bar plus n2 y2 bar. Okay. And this we can write as, if we divided it by the number of total number of moles, that means n1 plus n2, n1 plus n2. If you divided it by n1 plus n2, that means n1 plus n2, then it becomes small y, that is the molar y for the system as a whole, it equal to x1, that is the mole fraction of the component 1, and this is the mole fraction of the component 2. And x1 we can write as 1 minus x2 y1 bar plus x2. I replace or I express everything in terms of x2. Let us consider this equation as an important equation. Y is 1 minus x2 y1 bar plus x2 y2 bar. Again we can use this expression that from the Euler's theorem which we get, xi del y I del x k at T p n j j naught is equal to k 0. And this expression, if you just remember this expression and use this for this multi-component system, we can write x1 del y1 bar del x2. Here k is 2, we are using x2 del y2 bar del x2 is 0. Del x2 is 0. Where we have used, what we have used? You have used this relationship xi, this is the sigma, I is equal to 1 to r. For a two component system, it is x1 del y1 del x2 plus x2 del y2 del x2. So now in place of x1 I write 1 minus x2 del y bar del x2 plus x2 del y2 del y1 bar del y2 bar del x2 is equal to 0. Okay. Now you differentiate this equation, this one, 1 minus x2. Now we differentiate this equation with respect, here I will do, you differentiate this with respect to x2. If we differentiate with respect to x2, then what we get? Del y del x2 at constant temperature and pressure, what we get? We differentiate with respect to x2, that means first term is minus y1 bar, second term is plus 1 minus x2 into del y1 bar del x2 plus y2 bar plus x2 del y2 bar del x2. So you see what I am doing? I am now differentiating y with respect to x2 and I get del y del x2 is minus y1 bar, this one, derivative x2 minus 1 plus 1 minus x2 del y1 bar del x2 plus y2 bar plus x2 del y2 bar del x2. Now you see, if I compare this equation with this equation, now you see this plus this is 0. So therefore I get del y big Y, that is del y del x2 at T and P is equal to minus y1 bar plus y2 bar. So now I get these two equations. One is this one. So I use these two equations now. One is this one and another is this one, y is x1 y1 bar plus x2 y2 bar. Remember these two equations. If we solve these two equations for y1 bar and y2 bar, y1 bar and this y1 bar plus y2 bar is del y del x2 at Tp, and x1 y1 bar plus x2 y2 bar is y. If you solve these two equations, then what we get? These two equations if you solve, then you get finally for y1 bar, you get this one. Well, for y1 bar, you get y minus x2 del y del y big Y del x2 at Tp. The small y is the molar property y for the system as a whole. That means y divided by n1 plus n2. I am solving this equation and this equation for y1 bar and y2 bar. So I get this. Similarly, I get y2 bar is equal to y plus 1 minus x2 into del y big Y del y del x2 at T and P. Now this equation has got a very good geometrical interpretation. How it is that if I can plot this x2 versus any of the component, any of the mole fraction of any of the components. Let us consider here the component 2 versus x2. Y versus x2, that is the molar function, that means y by sigma n. In this case it is n1 plus n2. That means the molar property, if I just plot versus x2, this y can be anything. This molar property can be molar volume, partial molar volume, that then it will be molar volume, it may be volume, it may be Gibbs function, it may be entropy, it may be internal energy, enthalpy, anything. And if I denote this line or this point as x2 0, and if I get here that this is the line, this point as x2 1. Now x2 0 means x1 is equal to 1. So x2 0 means x1 1, and x2 1 means here x1 0. That is x2 1. That means x1 0. So here x2 0, here x2 1, here automatically here x1 1, x1. And if I get a variation like this, for example, this is the variation. That means this is the curve of y versus x2. Then at any point P, now if I want to know, that means any point on the curve P which has got a mole fraction x2, and the corresponding x1 will be 1 minus x2 and 1 minus x2 as the x1, obviously, because x2 x1 are related like this, x1 plus x2 is equal to 1. So at this point, if I want to know what is the value of y1 bar and y2 bar, this will follow this equation for a given value of x2, that any x2, what is y1 bar given by this equation, what is y2 bar given by this equation. So at constant temperature and pressure, if I have got the molar property y for different x2 and if I can plot it, then it is very simple graphically, that if I draw a tangent at this point, let this tangent is drawn at this point, okay, let this point is P and let the tangent is drawn at this point, and which cuts here at A and here at B. Then if I define this point as O and this point as O dash, then I can write AO, that means this intercept, the intercept of the tangent on this ordinate where x2 is 0, that is AO, that is equal to y1 bar. And the intercept of this tangent on this ordinate where x2 is equal to 1, which is O dash B or BO dash, BO dash is equal to y2 bar. Because you see what is AO dash? AO dash is y, you just, if you now geometrically if you see that this is the y, this is the y minus this one, and this is equal to x2 del y del x2 Tp. Del y del x2 is the slope of this line, del y del x2, that is tan theta. If this is theta, tan theta. So therefore this amount is x2 del y del x2 at Tp. So therefore this minus this, that means the length of this intercept AO is y1 bar, and similarly the BO is the BO dash is the y2 bar, that means this is the y2 bar. This can be proved that like this, that this is the this is the y at this point. So this part is added, so this part is 1 minus x2 del y del x2 bar, because if this is the x2, so obviously this is 1 minus x2, that means this length is 1 minus x2, whereas this length is x2. All right. So therefore we see that x2 and 1, that means this is this. So therefore we can draw a tangent, and sometimes geometrically these problems are solved, that at any point on this curve y versus x2, if we draw a tangent, these cuts or the two ordinates where x2 is 0 and x2 1, and these intercepts OA and OB, they can be taken as the partial molar properties y1 bar and y2 bar. So and this is valid for any component, for any partial molar property. Okay, all right. Now I will start a new property, that is fugacity. All right. Now we will start what is fugacity. Fugacity. Now you see this fugacity concept. First of all, I tell you, this the concept of fugacity will be given not with respect to a multi-component system, but I will first tell you what is fugacity for a single component system, because the concept of fugacity holds good for a single component system, which for any single component system which does not behave as an ideal gas. I will tell what fugacity is, because this concept of fugacity will be required to understand the dilute and ideal solutions. When there is a mixture of different components, whether they behave as dilute solutions or ideal solutions, that for that we require the concept of fugacity. That is why we will first start fugacity. Now we know for a single component system, we know for a single component system, what we know, that G is equal to H minus Ts, that is the molar Gibbs function, molar enthalpy, molar entropy. And we know that if we take dG, if we remember it, TdS minus SdT. We just recapitulate this thing again, and dH is du plus PdV, okay, and TdS and SdT. So obviously dH is VdP minus TdS, as usual you can write VdP, dH is VdP plus TdS. So therefore this becomes SdT plus VdP, because H is U plus PV. If you take dH is du plus PdV plus VdP, again the recapitulation of the earlier thing, the basic things, du plus PdV is TdS plus VdP. So therefore if we just substitute this dH, so we get dG is equal to minus SdT. So this we, well, SdT plus VdP. Okay. Now for a constant temperature, for a constant temperature, when temperature remains constant, we can write dG is equal to VdP. Okay, we can write dG at constant temperature, VdP at constant temperature. Now this is a very, very important relationship in thermodynamics, that is the molar Gibbs function for a single component pure substance, dGT is VdPT. At constant temperature dG is VdP. Now if we consider this system as an ideal gas, consider an ideal gas, an ideal gas, system as an ideal gas, then what we can write? We can write V as R bar T by P, where R bar is the universal gas constant. Okay, then we can write this dg t v dpi is like this. Dg t is r bar t by p dp. This is at constant dp at constant. So dp by t we can write as dgt as r bar t d of ln p at constant t, because dp by p is ln t. So this is the relationship which holds good for an ideal gas, So it has to be a single component system, and for an ideal gas, if this system behaves like an ideal gas, then this dg at constant temperature becomes equal to r bar t into d ln p t. Now it has been seen that in many thermodynamic relationships with multi-component system, it is very important to retain this function, this functional form. To retain this functional form is very useful, and it has been shown that this functional form has to be retained in many applications for multi-component system, so that even if the system does not behave as an ideal gas, even for system not behaving as an ideal gas, not behaving as an ideal gas, even for system not behaving as an ideal gas, if we want to retain this type of functional relationship in terms of this ln, try to understand, to express the molar Gibbs function as this, it is very useful. Then what we can do, we cannot use p, we can define a function f as a property which makes the same relationship for dg, that means the change in the molar Gibbs function at constant t for an ideal gas. That means instead of p, we defined a function f for non-ideal gas systems, so that the same relationship or same functional relationship for dg at constant temperature can be expressed. Then this f is known as fugacity. So you see, fugacity of a system is same as that of a pressure in an ideal gas. Its unit is same and its sense is also same. And we can tell this way that fugacity of a system does the same thing as the pressure of an ideal gas does with respect to the change in the molar Gibbs function. So this is the basic definition of fugacity. So from this it is clear that the limit of f by p, f is not p, but f tends to p when p tends to 0. Why? Because at very low pressure any gas behaves as an ideal gas. But if the pressure is increased, the deviation is there, so that the fugacity is not equal to pressure. So okay, so today I will end here. Next class I will discuss it in detail. Okay, thank you.